Here is a rule. Every reply this system drafts to a customer has to cite an article from the knowledge base, because a support answer with no source behind it is a guess wearing a uniform. It is a real rule from a real system, and every team has a dozen like it. So where does it live? Usually in 3 places, and I want you to notice what all 3 have in common. It lives in the prompt, in the paragraph that tells the agent how to behave. It lives in a comment above the function, addressed to whoever reads next. And it lives in somebody's head, the person who will catch it in review. Prompt, comment, memory. Every one of those is advice. Every one of them depends on somebody, or something, choosing to remember at the moment it matters. And when the agent produces a draft with no citation on it, not one of the 3 does anything at all. The draft compiles. The tests pass. It goes out. There is a 4th place to put that rule, and it is the one almost nobody reaches for first. You can put it in the type. Not a check that runs and complains. Not a test that fails afterwards. You change the shape of the thing so that a reply without a citation is not a mistake you catch. It is a sentence you cannot write down. The compiler will not let the program exist. Nobody has to remember because nobody is being asked to remember. This is the first of 5 episodes about gates, the machinery you put around code when a human is not reading it, and we are starting here for a reason that is mostly about money. This gate is the cheapest one there is. It runs in the time it takes to build, it needs no test data, no environment, no run, and once it is in place it costs nothing per use, forever. Let me show you the idea before I give it a name, because the name has done a lot of damage by arriving first. Picture a record describing a network connection. It has a field for the state, which is one of connecting, connected or disconnected. And then, because different states need different information, it has 5 more fields, each of which might or might not be filled in when it started connecting, the last ping time, the last ping identifier, the session identifier, and when it disconnected. Look at what that record permits. It permits a disconnected connection that has a live session identifier. It permits a connection that is connecting and has already disconnected. Those are not edge cases. They are nonsense, and the type says they are fine. Now do it the other way. Write 3 small records, 1 per state, each carrying exactly the fields that state actually has, and fold them into the state itself. The nonsense combinations are gone. Not rejected. Gone. There is nowhere to write them. That is the idea, and the name for it, from Yaron Minsky at Jane Street, is making illegal states unrepresentable. Now take it back to the support tool. Before, a draft has a body, and a citation that might be there or might be nothing. That is one field of doubt, and it will be checked in a dozen places, and one of those places will get missed. After, the citation is its own small type, and the only way to build a draft at all is to hand it a body and a citation together. There is no other door. Delete the loose constructor and there is no expressible program in which an uncited draft exists. An agent writing against that shape cannot produce the bad draft, not because it was told not to, but because there is no way to say it. That is the whole move, and it is available in almost every language you are likely to be using. So, what does this gate actually catch? For once there is a clean number. GAO, Bird and Bar, published at the Software Engineering Conference in 2017, and their method is the good part. They took 400 real bugs from nearly 400 public JavaScript projects, chosen by proper sampling rather than by eye. For each one they checked out the code as it was just before the fix, added type annotations by hand, and then asked a simple question. Does the type checker complain? Not would it have helped. Does it complain, on this exact code, before the fix? They ran it twice, once for Flow and once for TypeScript. Flow caught 60 of the 400. TypeScript caught 60 as well. 15%, both of them, with the true figure somewhere between about 12 and 19. 15% might sound underwhelming, so sit with what it is 15% of. These are public bugs. Every one of them had already been committed, had already been through whatever testing that project did, and had already been past human review. That is the paper's own framing, and the authors are careful to say it makes their design conservative, because it stacks the deck against the very thing they are measuring. So this is not 15% of all bugs. It is 15% of the bugs that got past the humans. When the researchers showed the result to an engineering manager at Microsoft, he said this. That's shocking. If you could make a change to the way we do development that would reduce the number of bugs being checked in by 10% or more overnight, that's a no-brainer. Unless it doubles development time or something, we'd do it. Now the other side, and a gate episode that only tells you what a gate catches is an advertisement. Between them the two checkers caught 63 of the 400, so 337 got through, and the paper does the work of saying what those were. They sorted every undetectable bug into categories, and one category swallowed the rest. 186 of them, 55% of the total, were failures to implement the specification. Widen that to every kind of specification error and you are at 78%. That is the sentence to take away from the whole study, and the authors say it plainly themselves. The type system checks what you told it. It has nothing whatsoever to say about what you meant. Which means the strength of this gate is not a property of the language. It is a property of how much of your intent you are willing to sit down and write into the shapes. We have a bug in this channel's own history that shows exactly where that ends. In the second series we built a support tool that logged an incoming customer message one line before it redacted the card number inside it. The redaction worked perfectly. It just ran second. Now ask the compiler about it. The thing being logged is a string. The thing being redacted is a string. The order in which you touch two strings is not a type error in any language I know of. It compiles, it always compiled, and it would compile in the strictest type system on earth. But here is the honest turn, and it matters more than the complaint. You can lift that into a type. Make the redacted text its own kind of thing, and make the logger accept only that kind of thing, and the wrong order stops compiling instantly. The gate could have caught it. It did not, because nobody had written the rule down anywhere at all, and a compiler cannot enforce an intention that has never been stated. That study is nearly a decade old, though, and its subject was human-written code. Does any of it survive machines writing the code? There is a paper published in August of 2026, accepted at a reliability conference, that gives the cleanest answer I have seen. The authors collected nearly 87,000 failing samples from 7 different models across 4 compiled languages. Just over 52,000 of those failures were caught by the compiler. Just over 34,000 escaped it and blew up at runtime. And the language breakdown is the thesis in one row. Rust, which has the strictest compile time checking of the 4, accounted for more than 23,000 of the compile failures, and the authors say plainly that this is because its checks are stricter. Then look at what reached runtime. Null pointer dereferences, Java, 140. Rust, 2, out of more runtime errors in total than Java had. In the language where a null cannot be written down, the failure caused by nulls essentially stopped existing. I want to be careful with that, because it is the kind of number that gets flattened into a slogan. Rust also produced the most compile failures of any language in the study, and the most runtime failures too, and its numeric overflows ran at 44% of its runtime errors against roughly 4% everywhere else, because it stops on an overflow instead of quietly wrapping around. The strict system did not produce fewer failures. It produced louder ones earlier. And there is a result in the same paper that should stop anybody who thinks the compiler closes the loop on its own. They fed the compiler errors back to the models and measured what happened. Depending on the error, between 5 and 15% of the time the code came back genuinely fixed, meaning it now passed the tests. Between about 53 and 84% of the time the error went away and the test still failed. The complaint gets resolved. The program stays wrong. Which brings us to how this gate gets gamed, and the answer is not clever, it is one keystroke. In C#, if the compiler warns that something might be null, you can put an exclamation mark after it and the warning goes away. That is the documented purpose of the operator, and Microsoft's own reference says the thing you need to hear, it has no effect at runtime. Nothing is checked. Nothing is fixed. The gate is simply told to be quiet. There are bigger versions of the same door, a dynamic type that suspends checking wholesale, a string standing in for a thing that deserved a type of its own, a build setting that mutes a rule everywhere at once. And the default itself is worth knowing, because most people do not, those null warnings, and the warning you get for a switch that does not handle every case, are warnings. Not errors. They do not stop anything until somebody explicitly turns warnings into errors in the build. Out of the box, this gate is advice, and an agent optimizing for a build that goes green will happily take the quiet door, because the quiet door also makes the build go green. Then there is the bill, and it is real. In that study, the median annotation needed to trigger the error was 2 tokens long, but the median bug took between 2 and 4.5 minutes of a person's attention to annotate, and that person was an expert doing nothing else. Multiply by a code base. Rust's 23,000 rejections are not 23,000 caught bugs, they are mostly an agent being sent back to try again, and somebody is paying for those attempts. And the deepest cost is not time at all. This gate only ever knows what you sat down and told it, so the work is thinking clearly about your own domain before you have written it, which is the hardest work there is and cannot be delegated to the tool that benefits from it. So here is the self-check, and it is small on purpose. Find one rule that lives in a comment, or a prompt, or your own memory. 1. Move it into a type this week and delete the comment. Next episode, the gate everybody already has, everybody already measures, and almost everybody is measuring wrong.